So, but I bet you're good with this. In your lecture notes, right before this, what we did, or kind of before this, what we did was come up with the density of a metal alloy that was a block. Now we're coming up with the density of something that's an irregular shape, and we're going to use displacement like you guys did your stopper. So notice we have the mass of your irregular piece of rebar, okay? That would be the mass of your stopper. We went ahead, you can kind of see two volumes here. Which volume, 13.5 or 22.4, represents when I put the rebar in there? Yeah, the 22.4. How am I going to get the volume of the rebar? Subtract, exactly. It's like deja vu, right? Oops. Maybe. I think my poor computer's saying, you have not restarted me for a while. Okay. So there is now this flat line. It's not showing us like a little curve like meniscus, but showing you the initial volume of 13.5. Put the rebar in, it went to 22.4. You told me by difference, I can get the volume of the rebar. We're going to do that here in a minute. The original data gave us the mass of the rebar. Like I said, it's easier to measure mass when it's dry. Yes. So we have different rounding. We've talked about we don't do as much adding and subtracting as we do multiplying and dividing, but here we have a subtraction. So how many people think we're going to round according to sig figs? How many people think we're going to round according to decimals? You're totally right. Okay. So show all of your work. The volume will be 22.4 minus 13.5. How much the water went up with the rebar minus how much the level of the water before the rebar. You guys told me decimals, so this shouldn't be too bad. I'm allowed 1 decimal, and so the answer is 8.9 milliliters. This is a good example of if we had gone sig figs, which would not be correct since we're subtracting, hopefully you guys would say 3 sig figs, 3 sig figs, 3 sig figs is my answer. We can make it, we can put a trailing 0 after the 9. That's not right, because we're subtracting. Okay. So density is a ratio of mass to volume. So simply, I don't think there's no hidden, like 2 different answers would be fine for this. Simply, we're going to put the mass that we saw on the first slide, that 69.658 grams of the rebar divided by the volume, which we got by difference, 8.9 milliliters. So get your fingers ready. We're going to go sig figs. How many sig figs in our answer? How many sig figs in our answer? So we look at the things we're dividing, and we're going to go with 2. You got it. So I got 7.8 grams per milliliter. Okay. I bet we're good with that. Gonna switch gears now. I want to do kind of a different type of problem before we go on to kind of factor label. I want to talk a little bit about mass percent. Percent by definition means parts per 100. Okay? So then by definition, if you give, and we're going to look at a Clorox bottle here in a minute, it gives the ingredient in weight or mass percent. Weight percent and mass percent mean the same thing. So what that means is it means X grams of the component A. See, you could have like mixed, in this case it's a Clorox, so it has a lot of water, a few active ingredients, okay? Mass of the component per 100 grams of the mixture, by definition. So here's our Clorox bottle. If we focus on this one right here, okay, we're going to talk about nomenclature in here. Nomenclature is how you name things, and before you guys leave Gen Chem 1, you'll be able to tell me what sodium hypochlorite is if you don't know yet. But the formula for sodium hypochlorite, and I usually write it this way, sodium, the element sodium. Hypochlorite is just 1 atom of chlorine, 1 atom of oxygen. We're going to kind of talk about how that makes your, what we call an ion, a polyatomic ion, floats around and connects with your sodium cation. But anyway, sodium hypochlorite is 7.4%. you're going to have to be able to unpack what 7.4% sodium hypochlorite means. So I kind of have been unpacking numbers for you along the way. When I say unpack, I mean to clearly show what's in the numerator and what's in the denominator. And the reason I kind of think of a divisor between my hands. The reason we need to unpack numbers like percent, clearly say what they mean, is so that we can use them as a tool in a problem. So that's coming up. Most notably, what's the density of water? About 4 degrees? Anybody know? Yep, 1.00 grams per milliliter or grams per cubic centimeter. It's the same thing. What we did yesterday, or in the one of your calculations that's going to be due for using your data, is we said we can restate this as 1.00 grams per exactly 1 milliliter. Okay. So again, you kind of see that pattern of thou shalt clearly show what units of the numerator, what units from the denominator, and the numbers that go along with those units. Well, instead of having 100 grams of mixture, usually we just have a random mass of mixture. Good luck getting exactly 100 grams. That thing we use for, by definition, weight percent or mass percent is X grams of a component, we'll call it component A, over 100 grams of mixture. Okay, again, you really going to have 100 grams of mixture? This actually tells you how we calculate mass percent. All we do is we take a mixture, okay, we take a certain amount of your mixture, we get a mass on it, we put that in the denominator, we get a mass on a component of interest, we take a ratio, and to get it in parts per 100, we have to multiply by 100. Now sometimes I like to say we're multiplying by 100%. You'll kind of see that in one of the problems. Let's see what that looks like. Oh, before we see what that looks like, I want to introduce something that you guys may not have been introduced before, but you're really close to understanding what it is. So we have percent, parts per 100. Then we have something called mass fraction. So mass fraction is simply weight percent, but you don't take it times 100%. So you can already see up here how you get to it. You just don't take it times 100%. I'm not going to rewrite it here. So do I have another slide on here? I want to finish that thought. If somebody says, I have a mass fraction of, let's go back to that, was it 7.4% sodium hypochlorite? Let's just say it was. Okay. So we said that means there are 7.4 grams of NaCO3, ClO3, excuse me, in 100 grams of Clorox. That is the mass percent, mass or weight percent. We could state that in terms of 1 gram. How many grams of sodium hypochlorite would we have in 1 gram of Clorox? Anybody?
0.074.
Yep. See how that works? She moved the decimal place over 2 places. See how these differ? This is mass. And actually at the bottom of this slide, these differ by a factor of 100. That's my only point there. They differ by a factor of 100. Mass percent, parts per 100. Mass fraction, parts per 1. So So if you're like me, there are some sort of problems in physical science I have to think about. And I'm like, oh, okay. If I think about it long enough, I'm like, I buy that. So let's work a problem. And what I would do with this problem is draw a picture. I'm going to draw a picture. Drawing a picture can be helpful. One of the things drawing a picture does is it makes me more confident about working the problem. So here's I have a lot of beakers when I make up solutions, and that's what I'm doing here. So there's my beaker. I'm going to make the solution, and I'm going to add 5.42 grams of sucrose. Feel free to abbreviate your problem however you want to. I mean, you can write SUC or SUCROSE. You can write the formula for sucrose. And it says that here, waiting to dissolve the sucrose, I am going to have 28.72 grams of water. When I combine the two, of course, I'm going to have a mixture. As long as all the sugar dissolves, I'm going to have a homogeneous mixture. And the question is, find the mass fraction and the mass percent of sucrose. So doing a problem like this is I would probably put mass fraction, sucrose, and I might even go ahead and say I know how to do that. On the previous slide, it simply says I need to know the number of grams of sucrose divided by the number of grams of the mixture. How do I get the number of grams of the mixture? Simply adding these two together. Okay? And then I'm done. So one of the things I want to do is to try to show you that things don't have to be complicated. Okay? All right. So it says then I need to know the mass percent, mass or weight percent. So what's the relationship, assuming I have the mass fraction, how do I get to the mass percent?
Mass fraction times 100.
Yes, exactly. So I'm almost done then. Okay, so here we go. Mass fraction will be the ratio simply of the component of interest divided by the total mixture. In this case, the mixture is a solution. So I'm going to go ahead and knock out the mass of the solution first. Do it separately. Now, you could all do it in one fell swoop. Whatever you do, I think I'm trying to kind of get across to you, you always have to show all of your work. Now, when you guys are doing your Alta homework, you don't. What I would do if I was doing my Alta homework, especially as you guys are going to be bumping up against problems, working problems with the calculator, I would have a notebook just for Alta, and I would keep my work in there. That will do a couple of things. That will get you started for how you're going to answer questions on the test. That will be, you can even come by and say, this is nice, is this enough to show my work to do well on the test? And that will also just, you can pat yourself on the back if you've done all that work. I just want to do that. Okay, so we're adding, so we need to round according to which one? Decimals or sig figs? Decimals. Yep, decimals, totally. So I can do 2 decimals. So 34.14 grams. I didn't have to drop anything, did I? So the fact that I didn't have to do any rounding, actually, I don't have to worry about the 2 types of answers. So now it's a ratio. Oh, check this out. So I'm going to pause for a minute. And Mrs. Amber Lehman Ruskell got these whiteboards for us. And so you get a whiteboard, and I want you to go ahead and show me what you would divide out. There's other things I want to use whiteboards for. We'll see if I find it annoying or fun. Okay. And white markers or whiteboard markers coming. Aren't they adorable? I'm just so excited. So I'll pass you out the markers. Let's see what you think. I'll pass you out the markers, and then I'll come around and give you the little whiteboard things. So I'm just looking at a ratio of what you would do to kind of finish up the problem there. Aren't they adorable? They're just so cute.
Thank you.
I feel like that last call on Jeopardy where they have to write down their answers. Woohoo! How'd we do? I went ahead and put up there what the ratio would be. This is what I was looking for. Any questions? So we put the mass of the component of interest, which is the sucrose. I would notice that on my answers, I didn't just leave it G from grams. I said grams of what? That's going to help you know what you're doing in the problem. So how many sig figs are we going to round it to? 2? No.
3, 4.
Not 4. I hear 3. I hear 3. We're going to go with 3 sig figs. And this is what I get. So, I see, I'm not going to, sometimes I'll have you show your boards, but I'm like, go ahead on your board, tell me what the mass percent is then. Yeah. How are we doing? Yep. Okay. So the mass percent would be 15.9%. 15.9%. Parts per million. The only problem I can see with this, we'll have to decide how I want to do this, is I can see you're trying to write 2 places. So, I mean, on your whiteboard and on that. But, any questions about that? 15.9%.
So that's our answer.
15.9%. It's the same sucrose solution. You could say it's 0.159 mass fraction. You could say it's 15.9% by weight. That's how that would look. I'm going to go back a slide. I'm going back to this slide because if you needed to unpack that 0.159 mass percent, here's how you would do. You would say that means in 1 gram of solution, you put that denominator, I have 0.159 grams of sucrose. So just hold on to your board for a minute. You like those? It's fun. And sometimes we'll have you show. Okay. All right. So I double checked. One of the things for this class that you should be kind of checking is when you log into Canvas, underneath it kind of tells you when things are due. Let me know if you're running this next. But the topic we just covered, part 4, actually part 4 is not due clear until from yesterday. We are working a little bit ahead in lecture as to when your Alta homework is due. Food for thought. At some point, well, food for thought, there are going to be times maybe between now and the next unit exam when you're going to have a whole crap load of Alta homework to do. So I would say, go ahead and I would do this weekend. It's not due until I don't want to set you up for problems. Okay? No, it's not due until So, yeah, we should do a little bit. I'm tempted, but no, we got to keep going. On to part 5, people. I've already used the term factor label method in here. Factor label or factor label method is just a process of working problems. Honestly, if you're not familiar with this process, you might as well buy into it early. Like my husband and I sometimes talk to each other, you know, we love y'all. And I don't know if he tells his students that, well, I'll tell you that. And we just say, just buy into it and do this process of working problems. What comes to mind is I have had, especially folks in nursing or folks that go on in the sciences say, I am so glad that you made me use this way of working problems. Okay? So let's go around the room. Oh, I know, let's use whiteboards. Use your whiteboards and tell me which of these, I think I only said 4, which of these 4 metric prefixes do you have to memorize? There are 4. Use your whiteboards. Do a little bit of kinesthetic work there.
There's 4.
There are 4. You can guess if you want. There is 1 big one and 3 little ones, if that helps. And you can even look at your neighbors. Yeah, if you got them, show them. It is like Jeopardy. People just hold them up. Yeah. Very good. So getting kind of the hand going. The 4, there's 1 big one, kilo, 3 little ones, centi, milli, and micro. Very good. Okay. Go ahead on your whiteboard. Which of these do you have to memorize? I'm digging this. Which one do you have to memorize? And when you got it, show me. Yeah. Oh, there's all sorts of game shows that do that. Yeah, memorize that. 1 inch is exactly equal to 5.4 centimeters. Yep. Very good. Okay. Now, to work problems using this factor label method of working problems, we count oftentimes on equivalency statements. So as I hold my hands up here, I have between my hands is an equal sign. So these are equal quantities. Okay. So these are equivalency statements. Do you have to memorize this one? Yes. Very good. Memorize it. Okay. So there are kind of 3 legs to, and it's not necessarily in this order, but 3 things to keep in the back of your mind while you're working problems using this factor label method. 1 is no naked numbers. You want to write that with this that no naked numbers. For every major quantity, you have the magnitude, the number part, and you always have the units part. No naked numbers. Okay. So I'm going to show you how you can take an equality and turn it into what's called a conversion factor. Okay? So we're going to use a conversion factor to get from point A to point B. We're just trying to convert numbers. So kind of the other thing, the last thing to kind of keep in mind is the units will drive how you set up your problem using this method. The units, just put blinders on the numbers, just focus on the units. Set up your problem. You should kind of string it along from left to right. And if your units are right, your problem is right. Okay? So, get your boards ready. So what do you think? Just thinking like 1 foot is equal to 12 inches. What if I have 2 feet? How many inches do I have? 24. And a half a foot. So show me what that is. Just show me how many inches in a foot. Or so how many inches in 2.5 feet? 2.5 feet. There are 30. Exactly. There are 30 inches in 2.5 feet because you figure 2 feet would be 24 inches plus a half a foot is 6, so 24 plus 6 inches, 30. Perfect. Now you might be like, why would you make something so easy difficult? But Trust me, down the road, this will make more sense. Okay, so let's see how we can get 30 inches. Let's see how we can get the same answer that we intuitively know using calculating method. Why is there a decimal here? Because there's a decimal there because I want to show that how many sig figs are there? There are 2. And I'm going to show you this here in a minute, but we had 2 sig figs in the thing we wanted to convert. So kind of keep an eye note of that. Okay, so how do we get to 30 inches from 2.5 feet using the factor label method? Here we go. We're going to start out with an equality. We know within the English system, 1 foot is equal to 12 inches. How many people think that's an exact relationship? Yes. Well, I would say so. It's exact. It's by definition. It's how we set it up. Thank goodness. Okay. So there's your equality. Now, one of the things we know about algebra is about math. If we divide both sides by the same thing, that's fair game. So I'm going to divide 12 inches by 1 foot and 1 foot by 1 foot. What's 1 foot divided by 1 foot? It is 1. It is simply 1. What happens if I've had things strung up and I'm multiplying terms? What happens if one of those terms is 1? Is 1. Like what's 15 times 1? 15. So the point here is we can take this ratio and stick it willy-nilly anywhere in things we're multiplying, and we're just multiplying by 1. No harm done. Okay? You got it. So there's that one. What if I divide both sides instead of by 1 foot, if I divide both sides by 12 inches? 12 inches by 12 inches is 1. Okay? So that means this over here is also 1. What's the relationship between 12 inches to 1 foot and 1 foot to 12 inches? The word I'm thinking of starts with an R. Ratio. They're both ratios. What do you sometimes say flip? What's reciprocal? They're reciprocals. Yep, they're the flips. Yeah, they're kind of the reverse order. Exactly. They're reciprocal of each other. So sometimes they'll stand up here. If you have an equal sign in between, I can make 2 ratios. I could go with this one in the numerator, this one in the denominator, or I can go with this one in the numerator, this one in the denominator. So it's like a PV or thing like that. I don't know. Anyway. So here we go. The way I like to work, I tell students I like to work problems is my first term is the thing I want to convert. In this case, that's 2.5 feet. So I usually put 2.5 feet over 1. Now this is where, if you haven't already, a few people have, go ahead and put that on your whiteboard. 2.5 feet over 1. Now look at this previous slide. You can either use the first ratio or the second ratio, and you want feet to cancel. What does that look like? Don't forget your units. Look into it. Yep. Perfect. No.
See, I
Normally, so do we all see why you need a decimal after the 30 now? To show that you had 2 sig figs in the term 2.5. That's fine. It's just that we have multiple terms. It's easier to know. That's what I'm trying to do. If you have your terms, okay. Yeah, if you're, I've read it very well.
Yeah.
If you have your terms turned around, that's fine. That's like some sort of property multiplication. What is it? The commutative?
Something like that.
And the one thing is identity property multiplication. Okay. So, but do you see where if we had put in the other ratio, what would the units here be? Feet squared per inches. Do you see what I'm saying? I'm going to put that over 1, and it just does not work. Let's see if it'll let me. Oh no, it won't let me do it. But see where I would have feet squared per inches in my end, and we needed feet to cancel. Okay. So that's a good place to stop. So pick up here on Wednesday. Yeah, and if you've already checked to make sure your sets, you're golden, you don't have to do this. Otherwise, if you haven't checked to see that you have Logger Pro, I want you to come over here. You got 5 minutes. Shouldn't take that long. That's right here.
You just gotta go up to the part and then, but it didn't accept it.
Oh yeah. Thank you. Yeah, if you could just, that'd be great.
I know how to do the basic operation.
Man.
Please.
Don't get it. Oh, back to later.
Yeah. Let's go down, you know, on Tuesday, Wednesday, I'll be back for lunch.
When is our first test?
On Thursday, so. See. Oh, let's make it teamwork.
Sorry.
Yep. good weekend. Thank you, ma'am. So what'd you guys think of the whiteboards?